Here's the solution to homework set number 4 for ECE 321 Analog Electronics. Here we're looking at transistor amplifiers. The first problem is find the Q point for this transistor circuit. To do that, what you do is you take R1, R2, and 12 volts, convert to the Thevenin equivalent. The Thevenin voltage is going to be R2 over R1 plus R2 times 12, giving you 4 volts. The Thevenin resistance is R1 in parallel with R2, giving you 267K. So these get replaced by these two elements. Then at the base to emitter, I have a diode. So base to emitter is a diode. Emitter to ground is a resistor. Emitter to ground is the 1K resistor. Emitter goes to collector through beta IB. Emitter goes to collector through beta IB. And collector goes to 12 volts through a 5K resistor. So this is the same circuit. Once you have the circuit equivalent, I can now analyze it. To find the base current, I just write the current loop equation around IB. So that's minus 4 plus 267K times IB plus 0.7 plus 1K times IB plus IC equals 0. Plus IC is 200 IB. Solving for IB, you get IB is 4 minus 0.7. That's the voltage driving the current. The total resistance then is your 267K, and the 1K is scaled by 201 because I have 1 plus 200 IB, giving 7 microamps for IB. IC is 200 IB, or 1.4 milliamps. Then the Q point is VCE. The voltage of the collector is 12 minus IC times 5K. VE is 1K times IB plus IC. And then VCE is the collector voltage minus the emitter voltage, 3.525. So there's your Q point, IC and VCE. And what that tells you is on the load line, again, there's 12 volts. I'm operating right here at 3.525 volts. That's probably not the best place to operate. I'd rather be closer to the middle. So that's problem number 2. Change R1 and R2 so that you are operating in the middle and you stabilize the Q point. So kind of going backwards. I know VCE should be 6 volts. That lets me find IC. That's going to be, if this is 6 volts, then the remaining 6 volts goes across the 5K and 1K. This voltage is 5K times IC. This is 1K times IC plus IB. And IB is IC over 200. Giving you, right here, IC is 991 microamps. IB is IC for 200, 4 microamps. To stabilize the Q point, I need to satisfy this condition. 1 plus beta times RE is much, much bigger than RB, or RB is much, much smaller than 201K. So 10 times is kind of a typical number. I want RB to be large, otherwise you're wasting power, but much, much smaller than 201K, so like 20K works. Once I set RB, I can find VB. Again, back on this circuit, I know IB, I know RB, I know all these currents. I can calculate VB, and that's just going to be 20K times IB plus 0.7 plus 1K times IB plus IC, giving 1.796 volts. That's the Thevenin equivalent of R1 and R2. So to find them, R1 in parallel with R2 is 20K. By voltage division, R2 over R1 plus R2 times 12 volts is 1.79 volts. And a trick you can do, if I take out the R1 up here, these two match. So I can substitute and find R1. Turns out that R1 is just going to be 12 over 1.7 volts times 20K, 133K. R1 in parallel with R2 is 20K, so find the R2 to make the total parallel resistance 20K, and I get 23K. So there's R1 and R2. This stabilizes the Q point and sets the Q point to 6 volts VCE, right in the middle of the load line. In Circuit Lab, I can check. If I build this circuit in Circuit Lab and do DC analysis, what I'll wind up with is the base voltage is about the same, collector voltage is about the same, emitter voltage about the same, VCE a little bit different. That's just because beta is 215 for this guy. I assume 200. For the 23904 transistors, Beta is guaranteed to be somewhere between 100 and 300. So if I design for 200, it might vary. So Circuit Lab assumed 215. It could be anything between 100 and 300. And you can also change that. If I double click on Q1, I can change it to see what it would be at 100, change it to see what it would be at 300, change it to be nominal. If you build it, it's going to be somewhere between 100 and 300. So that's problem 3. Problem 4 is where it gets fun. These are the two-port models. A two-port model is just a Thevenin equivalent. What I like doing is think about the two-port model that looks like this. You got the Thevenin equivalent at the input. Yeah, this isn't very good. There. Thevenin equivalent at the output. What test would you run to find each parameter? Whatever test you do on the two-port model, do exactly the same test on the circuit. To start with, if I want to find the input resistance, what I'll do is I'll short the output, measure the resistance at the input. Do the same thing in your circuit. Short the output, measure the resistance at the input, and I have 100K to ground in parallel with 50K to ground in parallel with 2K to ground, giving you 1887 ohms. So that's this number here, 1887. To find A in, this guy, AI B out. I apply 1 volt at the output, measure the voltage at the input. Doing the same thing on your circuit. Apply 1 volt at the output, measure the voltage at the input, and here I've got a voltage divider. It's going to be this parallel resistance over 2K plus the parallel resistance times 1 volt, giving you 0.934 volts. So that's this number, 0.934 V out. To find the output resistance, short the input, measure the resistance at the output. So I short the input, measure the resistance at the output. If it's not obvious, add like a 1 volt test voltage and calculate the current. In this case, the current is going to be 1 over 2K plus 1 over 1K plus 200 times 1 over 2K, giving you 101 milliamps. The resistance then is voltage over current. 1 volt drew 101 milliamps. It must be 9.8 ohms. That's the output resistance. Then to find A out, apply 1 volt to the input, calculate the voltage at the output. So here I do a voltage node equation. V out minus 1 over 2K, so it's this current plus that current has to add to 0. So that's V out minus 1 over 2K plus 200 times V out minus 1 over 2K plus V out over 1K equals 0. V out is 0.991 volts. So there's your two-port model. Now, a little bit of work, but that's how you find the two ports. Problem 5 is for a different circuit. Now find the two-port model. Same procedure. To find Rin, I short the output, measure the resistance at the input. If it's not obvious, apply a 1 volt test voltage. And the current then is 1 volt over 1500 plus 1 volt over 2K plus 200 times 1 volt over 2K, giving you 101 milliamps. The input resistance then is 9.88 ohms. To find the input gain, apply 1 volt to the output, calculate this voltage, and here you can kind of guess. If I get 0 volts, it balances, because the current then is 0 plus 200 times 0 is 0. 0 works, AI equals 0. To find R out, I short the input, in which case IB is 0, 200 IB is 0, so all these go away. I just see 5K. And to find A out, apply 1 volt at the input, find the V output voltage. So the current then is going to be minus 1 over 2K, or actually current is 1 over 2K going down, making this 200 times that current. Voltage is I times R, so it's going to be 5,000 times 200 divided by 2,000, 500. So here's the two-port model. Let's see. Problem 6. Given the same problem we had in problem number 1, find the two-port model, or the AC model. In this case, I'll take this circuit and redraw it. I've got the input goes right here. I see a 400K to ground, that's this guy. I see 800K to ground, that's this one. I see a diode to ground. So here's your diode. The resistance is your Q point at DC, 0.026 over the Q point. This number can vary. It's anywhere between 1 to 2 times 0.026. Let's see, Circuit Lab uses 1, sometimes it's 2. Some diodes are like 1.4. I use 0.026 just to be consistent with Circuit Lab, giving you 3685 ohms, and takes you to the emitter. And again, it kind of helps to label these points. Emitter goes to collector through beta IB. Collector goes to ground through 5K. And this is for AC 0 volts, because this is 12 plus 0 sine omega t. I'm doing the AC analysis. Now find the two-port model. At the input, it's kind of obvious. I just had these three in parallel, 36, 35 ohms. Okay. Let's see, the input voltage is 0. There's nothing driving it. Output resistance is 5K. If I short the input, IB is 0, 200 IB is 0, I just get 5K. And the gain, apply 1 volt at the input. If this is 1 volt. The current is 1 over 3685 times 200 times 5K with the minus sign. So the gain is minus 271. In Circuit Lab, I can check. Do I have my circuit in Circuit Lab? Nope, I didn't do it. In Circuit Lab, what I can do is build this circuit. Again, you might want to build the actual circuit. But what I'm going to do is I'm going to add a resistance in series right here. Add a resistance at the output. And if I vary those, I can find the parameters. To find A out, what I'll do is make this 0 ohms, this large, like 10 meg. Make this a 1 millivolt sine wave at 1 kilohertz. Measure the output voltage. In that case, what I got was the output voltage was 257 millivolts, so that's the gain, 257. It's actually minus 257, but I can't see the phase in Circuit Lab. To find the input resistance, I'll make R out 10 meg and make this, let's see, what did I make it? 6,000. And now find the output voltage. And what you're doing is, again, you got your two-port model. So where's my two-port model? Got my two-port model right here. Yeah, okay, got a two-port model. This guy. What I'm going to do is add a 6K resistor in series. And what that's going to do is by voltage division, it drops the voltage. If the voltage goes down, then the output goes down by the voltage division. So give an idea how to solve this in Circuit Lab. This is kind of what you do in the actual lab. You build the circuit. This is the common emitter amplifier. I want to find the gain, the input resistance, output resistance. So to find the gain, I'll take the output. Go away. Make it something large, like 10 meg. Input resistance 0, and make the input, I'm having a hard time with my mouse, 1 millivolt at 1 kilohertz. Now do a simulation. I'm going to simulate, do a time domain, starting at 3 milliseconds, ending at 5 milliseconds. That's 2 cycles. Waiting 3 milliseconds to let it settle out. And run a time domain simulation. That's what I get. If I look at the peak is wrong. That's because C4 is wrong. 100 microfarads. Try it again. Simulate it. And the output peak is 256 millivolts. That's the open circuit gain. That's A out. This is a gain of 256. Now to find the input resistance, what I'm going to do is change this guy. So by voltage division, if this gets bigger, say if this is equal to Rn, the voltage will drop by half, so the output should drop by half. So let's try that. Let's make this 6K. Come on, mousey. Run the simulation. And now I'm getting 98 millivolts. That 98 millivolts lets me calculate Rn. And if you do the calculations, it works out to be this. It's the voltage, the new voltage over the original gate voltage minus the new voltage times 6K. That's my test resistance. The input resistance is 3727. Now to measure the output resistance, what I'll do is I'll change this back to 0, change the output resistance to say 5K, and now measure the output. If this is equal to the output resistance, then by voltage division, I should be at half the voltage. Rerun it, and I'm now at 131 millivolts. What that tells me, I guess 134 when I did the solutions. The output resistance will now be the original voltage, A out, minus the new voltage over the new voltage. If this is half of that, I'll just get 5K. This is actually 4580 ohms. So that's kind of how experimentally you find the two-port parameters. Build a circuit and do a couple tests. Calculated gain versus simulated gain. Again, in pretty close agreement. Problem 8 then says look at cascading 3 common emitter amplifiers. So here's one CE, here's the second common emitter, here's the third common emitter. Cascade them, what do you get? Well, the input impedance, or input, is pretty simple. It's just 3635 ohms. The output resistance is 5K. I short the input to ground, makes this 0, makes this 0, makes that 0, makes this 0, makes that 0, makes this 0. I just get 5K. The gain is the one you got to work for. To get the gain, apply 1 volt at the input. This becomes minus 274 volts. By voltage division, this becomes 31 kilovolts. No. By voltage division, this becomes 114 volts. I did that wrong. Erase. There we are. Becomes 114 volts. Times minus 271 becomes 13 kilovolts. No, 31 kilovolts. 31K. By voltage division becomes 13 kilovolts. There's a minus sign there. Times minus 271 becomes minus 3.5 megavolts. So that's the gain. And here's the calculations. So this is your two-port model. Number 9 is remove this capacitor right here and see what happens. If I do that at the input, I see R2 to ground, R1 to ground. So here's VN. Base to emitter, I've got a diode, which is RF. Emitter goes to ground through 1K. Emitter goes to collector through beta IB. Collector goes to ground through 5K. So there's your circuit equivalent. And notice what this looks like. At this point, I see 3685, and the resistance down here looks like 1K times 1 plus 200. Because for every milliamp going through IB, I get another 200 milliamps flowing, giving you 201 times the voltage. 201 times the voltage makes it look like the resistance is 201 times bigger. So this looks like a 201K. From the left. So the input resistance then is 400K in parallel with 800K in parallel with 201K plus 3685, giving 115 kilo ohms at the input. AI equals 0. If I apply 1 volt at the output, 0 works, because if this is 0, IB is 0, this is 0, everything's 0. Output resistance, if I short the input, IB is 0, this is 0, I just get 5K. The gain then, if I make this 1 volt, IB is 1 volt divided by 3685 plus 201K times 200 times 5,000, giving you minus 4.86. So there's your two-port model. And that's homework set number 4 for ECE 321 Analog Electronics.